recording, start recording, minimize. Hello everyone and welcome to a very sleepy edition of Handmade Hero. I did try to go to bed early last night. It did not work. I was able to have a midnight snack of cheese and almonds, which was tasty. But that means that I am bleary-eyed. I did have some coffee, and we've been chatting for about 20 minutes that we should have been programming for here as I attempt to wake up. And hopefully now we are at the point where we could actually do some reasonable coding. But there's really only one way to find out, and that is to try to do some reasonable coding. So, welcome to Handmade Hero, the show where we code a complete game from scratch, live on Twitch with no engine and no libraries, even when we are falling asleep, ladies and gentlemen. That is our commitment as the Handmade Hero team. That is our commitment to you. So, if you want to follow along today and you are not as sleepy, today is day 83, so unpack the source code for day 82, and that is what I am starting with, and if you want to follow along, that is what you should start with too. Now, we left off yesterday with a little to-do that I said I didn't have time to go over, and so you know what? We kind of need to go over that, right? Don't know if you guys remember. Also, it is high allergy season here, so the amount of times I will blow my nose in the stream is going to be staggering. That's just something you should be aware of. So that is going to be like a continual occurrence. I know, it's delicious. Anyway, so what I was talking about yesterday, well, you know, for those of you who might have missed it, what we did is we made it so that we could cache bitmaps and then use them. I realized we have a ton of little heads. I don't know why I left all those heads in there. They're just kind of little familiars who are floating around. Hi there, familiars. But anyway, that bitmap in the background there, what we basically did is we made it so that we could do caching of bitmaps on the fly. So we could basically, anything that we could have drawn to the screen, we can now draw into a bitmap. And so that's like a bunch of stamps that we put together to make a ground texture. And it was really slow to do that because we don't have fast rendering routines yet. We haven't written any. We just have a really simple bitmap copy routine, which is not optimized at all. And so that was really slow and it tanked our frame rate. So I was like, well, we could just cache the results of it and then draw it. And that's what we did. And there it is, right? But we haven't talked about what to do with the alpha yet, right? And so I kind of wanted to take a second to just talk about what that means so that we can kind of see, you know, what's going on here. So let's do that. Let's see if I can, oh, for some reason, and I don't know the reason, my pen does not seem to be working. Why does my pen not seem to be working? Let's see here, pen. There it goes. You know, USB, you just unplug it and plug it back in. All right, so day 83, there we go. So, you know what? It's not really working. It's actually going through mouse emulation, isn't it? Seriously, people? Is that where we're at? All right, well, you know what? Let's close Mischief, and we'll see. We've got that little weird thing showing up. You gotta love Microsoft Windows, people. You gotta love that sort of stability. It's getting more Linuxy every day. Yeah, this is totally untractable. Why have you ruined the Handmade Hero Blackboard? Why? Can we ask that question? Why would you do that to us? And I don't know. Well, we're not off to a good start, and I'm sleepy already. You'd think they could, you know, cut me some slack here. Yeah, so it's totally messed up. Well, I don't know what to do about that. I guess we'll have to take a second to actually try to figure out what's going on. I have no idea why it would just suddenly stop working, other than that's the sort of thing that happens with computers these days, even though nothing has changed. You know, shouldn't we have like a Wacom driver thing in here? Yeah. So the tablet driver was not. So let's take a brief moment and just point out this is what I talk about. You know, we've said this multiple times on the stream where I'm just like, what is going on with computing these days? Like, nothing has happened on this computer. It is exactly the same as when we left it yesterday. Like, nothing happened. So how do people manage to engineer software so bad that when nothing has changed, all of a sudden a driver is gone, right? It's just, it's ridiculous. And the quality level just keeps going down, and down and down. It's awful. So yeah, all right. This is going to be the worst drawing ever. I'll try to do it as well as I can, but it's super hard to control because it's not actually reading the tablet. It's treating it like a mouse, so it's all ugly. I'll do the best I can, and then I guess someone please remind me at the end, or send an email maybe to remind me to try and get this machine to re-recognize the tablet that it was recognizing just the other day. So if we take a look at what was happening before, right? We wrote some code where we basically, we have our draw bitmap. This is draw bitmap here, right? We have a draw bitmap call, and what that does is it takes a bitmap that has it has an alpha channel in it, right? Which is like a mask, or we're using it like a mask, to tell us where the bitmap has data we actually care about and where it doesn't. And the reason for that is because we don't want everything to be square, right? We want to have things that have shapes in them, and when we draw them to the screen, right, if there was stuff underneath, if there was some stuff here on the screen already, we only want to put this image, right, where it actually should go. We don't want to overwrite, like we don't want to see, you can imagine if we were to not use the alpha channel, there'd be like a square of emptiness that would follow this thing that we put in there, right? And we don't want that. We want it to cleanly to composite those edges, right? And that's why we need that alpha. So that was working fine. We got that working, and the way that we did that, again, is using our linear interpolation, right? Again, like I said, most important equation in game development, basically. Using linear interpolation, what we did is we said, all right, we have an alpha channel, right? The alpha channel is encoded as a byte. It goes from 0 to 255. And that 0 to 255 number tells us how masked the area is. 0 means don't show what's here at all. So that's like this area. 255 means full show. Like that's the complete opaqueness. And then in between are like gradations of blending, and that allows to have anti-aliased edges or like sort of transparent, like partially transparent things, right? So we can do some transparent effects there too. We haven't really taken any advantage of that, but we could use it, right? And so that all works just fine because we basically export things in out of GIMP that have that, or out of Photoshop or whatever, and we use those bitmaps to composite to the screen. But what we wanted to do yesterday was basically have a two-step process, right? Instead of drawing bitmaps to the screen and just drawing bitmaps to the screen, drawing them, what we wanted to do was take a bunch of bitmaps, so same scenario, right? Like so. We want to take a bunch of bitmaps, and instead of drawing them to the screen, we wanted to do it to like an intermediate buffer, right? So we want to draw this to some other buffer here, and then eventually later draw it to the screen. And the reason we did that is so we could save the work. So if we did like, let's say there's 100x of these sort of blits into here, we wanted to save that work and then use it again later, right? But what that means is we have to be able to produce an alpha channel for this intermediate buffer, right? So this had alpha that came from Photoshop or some other place, right? This doesn't need alpha, right? This doesn't have to have alpha at all, because it's just getting displayed on the screen. It's not getting composited with anything else, and the alpha isn't used by Windows to do anything. Windows doesn't need to know our alpha channel. It just needs to know the color channels, right? But this right here, where does this come from, right? How do we get alpha here? And so we just want to take a quick second to think about what we need that alpha to be, so we can make sure that we fill it in right. And that's kind of where we left it yesterday. right? Because we got everything working, but we hadn't really figured out what we wanted to do with the alpha channel. And so I'm just going to say a few things about it, and then we're going to see what it should end up being based on that and try it, right? So I guess what I would say is we can have some pretty straightforward things that we would want to have happen. The example would be, I'm going to use the numbers 0 to 1, since that's how we actually translated the alpha in there before, because basically we had, the real value of these is 0 to 1, and we're just encoding that in bytes as 0 to 255, right? So this is in integers, and this is in floats basically, or reals, right? So if we're talking about the 0 to 1 thing, where 0 is completely transparent and 1 is completely opaque, and everything in between is some gradation thereof, and we're encoding at 0 to 255, if we need to think about that. Whatever comes in and whatever is already in the buffer is what we're working with, right? For any given pixel, when something's getting drawn in here, we've got two things. We've got the source alpha, right? Which I guess we could call source alpha. And we've got the destination alpha, right? That's the thing that's already in the buffer, right? So the destination alpha. Now, we know that when we start out, we want all of the destination alpha to start at 0, right? Because if we had this buffer and nobody drew anything into it, we would want it to be completely transparent everywhere, because that means there's nothing in the buffer. So if we were to blit it to the screen later, we would want to see nothing. It should not affect anything at all, right? So we know that the destination alpha defaults to 0. So what we can say then is, on that first blit that comes in, the first thing that comes in, if you just did one bitmap and blitted that to the buffer, then blitted the buffer to the screen, you'd want it to be exactly the same as blitting what was in that initial bitmap directly to the screen, right? We don't want it to modify at all when it comes through here. So basically, like the first time, we could easily say that we just want the destination alpha to be equal to the source alpha, right? So that's kind of a requirement that we would have for this, is that if you just blitted one thing, you want them to be equal. Okay. So then what we really need to talk about is what happens the second time, and subsequently after that. Man, it's hard to draw with this, with no pen driver. So if we want to talk about what happens the second time, then really what we're talking about is what happens when destination alpha has some non-zero value in it, right? Because we know here destination alpha is already 0 at the beginning, so it's just basically a copy through there, right? So the second time through, and maybe I should write this slightly differently, like maybe I should say that actually this is, that assigns destination alpha from source alpha. So the second time through, what we want to have happen is, if there obviously was a 0 in there, so we could say if there was a 0 in there, then we want it to do exactly what it was doing before. So anywhere that hasn't been touched, it should still operate exactly as the first time, right? Because the pixels shouldn't, each individual pixel is kind of like its own buffer in some sense. So if there's a 0 in there, it should be operating the same as if it's the first time. Now, if there is a 1, so if source alpha equaled 1, right, then we also know, no matter what happens, the destination alpha should also equal 1, right? Because if I'm taking something totally opaque and blitting it over the top of things, I want to have that result be totally opaque as well, right? Similarly, if source alpha was 0, we would want destination alpha to be whatever it was before, right? If the source alpha is not, if there's nothing in the source image at that point, we don't want to modify whatever was in the destination at all, right? So if the source alpha is totally opaque, it should just overwrite it. If it's totally transparent, it should ignore it. So now all we really need to think about is what happens. That's pretty clear. What we really need to think about is what would happen when there's other values in here, right? And so, it's kind of hard to conceptualize, because it's not clear really what the operation equates to, if that makes sense. So let's say we had two things. So let's say we had SA equals 0.5 and destination alpha equals 0.5, right? So this is a half transparent thing that we drew in there. And now we've got a half transparent thing that we're drawing on top of it, right? What should the destination alpha be there, right? Should the destination alpha be half again, right? Should it be, oops, man, drawing with this pen is hard. In other words, should the destination alpha be 0.5 because that's, what was drawn on here? Should this kind of work at whatever the remainder is of here? So if we had 0.5 and we drew 0.5 on it, should that actually give us another half again? So should destination alpha become 0.75, right? Meaning that, like, let's say here's 1 and 0, and we're saying that this is the level that's currently in there, right? 0.5. Should the remaining range be what's used with the, with what's coming in, so that we're going 0.5 of the way up to transparent, right? And so, would we want this to basically produce that value, right? Going halfway there. It's almost impossible to draw with this thing. This is awful. Windows, I hate you. You make my life miserable. All right, so Windows is like the allergies of computing. Like, you can live with it, but it makes you unhappy every day. All right, so let's see. So, which of those two do we want to do? And unfortunately, like, even thinking about it now, I can't think of a really important motivating case here to really even know what we would do. So I'm going to look at it from the standpoint of the things that we actually have working now, which is, what we're actually using the alpha for. And that is for edges, right? We're trying to alpha blend our edges to make the edges smooth. And so the way that we're really looking at alpha is essentially as if it was coverage in some sense, right? We're really kind of looking at it mostly as saying, if there was a pixel and an edge was passing through that pixel, we are setting the alpha value to be, whatever that portion is there, right? So like if it covered 0.5 of the pixel, the alpha should be 0.5. That's sort of how we were looking at it, because we're not actually using it for transparency anywhere. We're just using it for edges. So when Photoshop, when you paint as a paint a brush through there, that's what it's doing. So you get into this kind of problem where you say, well, okay, if it's coverage, what we really would like to know is what part of the pixel was covered, right? Because you can imagine two scenarios. Let's say I had one bitmap that covered that part of the pixel and another bitmap that covered that part of the pixel, right? And if this is 0.3 and this is 0.3 coverage, then clearly when those two things drew on top of each other, you would want that pixel to become 0.6 because they're both covering different parts of the pixel, so you want to produce essentially that amount of coverage, right? But you could imagine another scenario where one thing was covering this much, and that's 0.3, and another thing was covering almost exactly the same part, right? 0.3. And in this case, the coverage when you composite them, is going to be actually redundant. And so it's actually going to be something like more like 0.5 or 0.3 still, because maybe this covered everything that this covered and so on, right? So this problem is why you end up with things like multi-sampling, right, in hardware that tries to do stuff like, okay, we actually take many samples per pixel so that we can kind of tell where the coverage actually was instead of reducing it down to a single number. But we're not going to go that far because that has a lot of extra implications, especially in terms of performance, memory footprint, all these sorts of things that we can't afford. So what we're going to do is say, all right, let's just pretend, for sake of our compositor, that what we want to do is let's just assume that the coverage is non-overlapping. So let's just say that the two coverages were the same, were the same, and or rather, let's how should I put this? Shouldn't exactly say the way. Let's assume that we are not trying to compute some absolute coverage, actual real coverage result that would require us to do multi-sampling, and let's just do something that will allow us to produce reasonable coverage in some other way, right? So the first problem we might have is if we just add them together, right? We would end up in a situation where we would overflow, right? So let's say we have two things that each cover the whole pixel, right? We add those two together, and this is one, we would end up with 2, right? Now that's not necessarily a problem because we could just clamp the value from 0 to 1. So we could allow it to overflow, and that would be like this model, right? That would just be saying all of the coverage is assumed to be separate, and so we're just going to go ahead and add them and clamp, right? So we could try that, and we could maybe try that and see what happens, right? So that's add and clamp, right, for destination output. The other thing we could do is this method right here, which sort of is the same. It's saying, let's assume that the coverage value is talking about covering the part that hasn't been covered yet, right? And so if we wanted to do that, what we would do is say, well, all right, we've got 1 minus. We want to know what's the leftover, right? We want to produce this region, right? So we want to do 1 minus the destination alpha, right? Which is saying how much do we have left? And then we want to multiply that by the source alpha to figure out how much of it we're going to use. That's the part that the source alpha contributes. And then we add that to whatever the existing destination alpha is, right? That's exactly this case here. This was the destination alpha, so this is 1 minus the destination alpha, this region up here. And then we're just taking however far we should go in that region and adding it back to the bottom, right? And that seems maybe a little better to me because then we don't have to do the clamping, so it's kind of like a more consistent thing. So I'd like to try that one as well. If you multiply that out, right, what you get is SA minus, right, I'm just doing the distribution here, SA dA plus dA. So the other way we could have phrased this is SA plus 1 minus, excuse me, sorry, putting dA here. I'm just pulling this dA out, 1 minus SA dA, right? So there's two ways we can actually phrase it. We can phrase it in terms of collapsing the dA term and using 1 minus the source alpha, and we could phrase it in the other way, which is doing 1 minus dA on the source alpha, right? So we can sort of pick who is the one who's being inverted. Make sure I do that right. I'm very sleepy this morning. SA minus SA dA plus dA, that's good. SA, and so we're pulling this out here, and that's 1 minus SA, so that's fine. And so so that's what we've got. And the only reason I was showing that is because we may already have this value pre-inverted. So if we wanted to fuss with that, right, I'm going to go ahead and kind of lean on the loop live code editing a bit here. I'm going to go ahead and do this so that we can kind of see what's going on. So if I come in here to our draw bitmap routine, it seems, if we take a look, we already have that 1 minus SA term, right? We've already got that on there. And so if you think of that term as inv SA, I'm just going to call that inv SA for now. Inv SA. Inverse is probably not the best term, but sometimes I'm not sure what the 1 minus would really be called, right? So if I change that to inv SA, right, nothing will change. We're doing the exact same blending equation there. Of course, I guess now that I think about it, we need to rerun the blit every time. So what we could do too is let me draw a test ground. Let me actually call that every frame. So we'll tank our frame rate again, but that way it'll update continuously for us, right? So if I just put this in here, right, there we go. Now we're drawing it every time. So if we, does draw test ground, but draw test ground doesn't clear the image. Yeah, so I can't keep doing that because otherwise, you'll get that sort of, Well, so I guess what I'll have to do is actually put in a draw rectangle call to clear it, right? Draw test ground that we can then remove later. So it would be this, right? Where we're drawing to the buffer and clearing it, right? And we'd want to clear it. Oh, and you know what I could do too? I could use 0 size for that. But yeah, so let's just see what happens if I do that. There we go. There we got our black fringe back. Okay. So now it's going, and you can see it's going much slower because it's not actually caching the bitmap. So let's go ahead and play with that draw bitmap now. All right. So in my draw bitmap call now, what I want to know is what should happen with this alpha channel, right? And if we take a look at what we wrote out here, I said it was SA plus 1 minus SA DA, right? And if you look, that's exactly what we were doing with everything else. We're just doing the inverse SA times the destination, right, plus that SA, right? That's exactly what we're doing. So, all right, so if I just, let's see what happens if I just go ahead and use that as our compositor. That's not quite right. That's right. We've got these in 2 different spaces. I forgot about that. So unfortunately, these are still all 0 to 255, aren't they? So DA is in a different space than SA in this case, which is not what we wanted. So what we kind of need to do here is we need to actually save SA in that case. So I guess we'll have to sort of introduce maybe this, for example, right? If we were to load them all out, and then I grab sort of like so. So if I were to keep them in the right space, and then I just make a real valued version of the source alpha, where we still have what the source alpha is in 255 land, right? That would allow me to do what I need to do here to allow the blending to work properly, right? So now everything's in the same space. We don't have one that's been normalized and one that's in the range of 0 to 255, which isn't going to work. So I believe that would give us back to, all right, not exactly yet. I believe that would give us what we wanted, so that stuff is now, you know, in that correct space. So when we load out the SA, now that's a number from 0 to 255. We divide that by 255 to give us a number between 1 and 0. We make the inverse of that by subtracting it from 1. But obviously I made a bit of a faux pas there because now we have an amazing rainbow pixel screen, which honestly is kind of a little bit mesmerizing. But yeah, so what did I mess up there? I took out the source alpha. I did in fact divide it by 255, which is what we wanted. So that turns it from 0 to 1. The C alpha is just that coefficient so that we can like dim things, right? So that's fine. The destination alpha is getting read out as a number between 0 and 255 there. And I think, oh, there it is right there. I forgot to put it, you know, I forgot to replace that with the new value that we computed. Okay, so there we go. So at least our blit is working now properly. So now we just need to get our other destination alpha stuff to be correct. So if I composite these two things together, that right, okay, there we go. And that one still needs to be the source alpha because that's actually the blend. So it would be, you know, that way. All right. So given that, that is that first method that we were talking about, right? That is the method that we wrote here, right? The SA plus 1 minus SA DA, right? That's exactly this. And so the question is, does that produce the result that we expect? And the first question is, well, you know, is there anything objectionable about the way that composite is working? And, you know, if we take a look at what happens in these sort of edge regions here, what I'd like to do is maybe take a look at what they look like in GIMP to see sort of what would be a reasonable thing to have occur. Now, if I go and open up, let's see, start Handmade data. If I go and open up one of these that we're using in GIMP, so I can actually view what its edges look like, I'm going to go ahead in here and make an actual thing that is essentially the same as what we have on the screen. So we've got a half bright thing, 128, 128, 128, right? So I'm going to take a layer here and just fill it with that. So we've got that essentially, right? And so that is what one of these looks like when we composite it, just one of those sort of splats onto the screen. And similarly, if I go in here and I open as layers some more of these, right? I'm trying to think of which, just trying to make sure we get a bunch of them in here, right? So you can see some of them do have like darker regions. Ground Zero doesn't, right? That one doesn't as much. That one does have some darkness to it, and so on. What I'd like to do is say, okay, let's take a look at one of these ones that doesn't have any darkening fringes around it. And let's just use that one for the compositing. And let's make sure that our alpha equation that we were picking there doesn't produce a bad sort of fringing effect. Let's make sure that when you layer these on top of each other, it looks okay, right? In order to do that, this is ground00.bitmap is the one that I had. So what I'm going to do is in that draw test ground function, I'm just going to go ahead and see I'm going to go ahead here and see what selection we were using. So this is grass. I'll turn off the grass entirely, so we don't have that, right? Let me bring that back up here. So grass is gone entirely. Oh, whoops, sorry. That actually also draws the stone. So what we want to do is turn off the grass entirely here, like that. And then we also want to, well, in fact, you know what I could do is just say, all right, you know what? Here's our else clause. There we go. So we're just going to take that first stone bitmap and we're going to use that, right? So what you can kind of see here is if you look at what happens, this didn't have any of that darkness in it, right? There was no, when you composited this on, this doesn't have any of that darkness on there. But if you look at what happens with the actual bitmap, you see all of that darkness in there, right? And so the question is, what happened there? Is our alpha equation wrong? Why are we getting that? Why are we getting that darkness, right? And the other thing we might try just to see, right, is what would happen if we turned off that. What would happen if we turned that off, basically, right? What would happen if we said we don't actually want? Let's see here. Draw bitmap. Sorry, I'm getting very sleepy today, so it's a little sluggish. What would happen if we just said, all right, the alpha is always just going to be 1, right? So what does it look like if we just always put in that 255 value there, right? So if I restart it here, right? And you can kind of see, you can kind of start to understand what's happening there. What we're getting is we're getting the black of the cleared buffer. So the buffer that, when we cleared it initially to just have nothing in it, what we're getting is that black color of the buffer is bleeding through to our result. Does that make sense? And so that can kind of guide us towards fixing what's wrong with our compositing so far so that we won't introduce that black at the edges. So again, I picked a real bad episode to be talking about the math of alpha compositing because we are still, because this pen doesn't work at all. Oh, and you know what I should also do? Let's double check that add and clamp doesn't work either, right? The other thing that we were thinking of. So add and clamp, if we were to do that, again, here's, oops. There we go. Add and clamp, if we were to do that, that's what we're currently at. And if we were to do add and clamp instead of this, that would just be A equals dA plus SA, and then we'd just say if A is greater than 255, A equals 255, right? We'd just full on clamp it. And you can see that we still get the same problem, right? So it doesn't actually matter which of those two we did, it still doesn't work, right? Okay, so what can we do here? What's the problem? What's going on? Well, I don't know. Let's go back to the blackboard and see if we can figure it out. So what's happening is we're getting color bleeding through. So we don't necessarily know if it may not be our alpha calculation that's at fault here, right? It could be that we're dealing with the the colors incorrectly, right? So let's think about what was happening there. What was happening there was we had a color that was in the buffer, right? So here's the source color. The source color is 0, right? And then we had a destination, and I'll put the source alpha here, right? So we had a source color, and let's just say we're looking at one channel, right? Like the red channel or something. So in fact, I could make that more explicit. So let's say we had the source red was 0, right? Then we had the source alpha, and the source alpha was some, percentage. It was 0.5. It was on those edges, right? And so we have the source, we have the source color being this. We have the source alpha being that, and then we're compositing against. Oh, I'm sorry. Again, too sleepy today. This is the source. So the source red is some color. It's 0.7 or something like that, right? And the source alpha was some, portion that was 0.5 or whatever it was, right? And so then we have the dest red, and the dest red is cleared because the buffer doesn't have anything in it, so it's just cleared to 0. And the destination alpha has nothing in it as well, right? So what's going to happen when we do this composite, right? When we do this blend, what we're going to get is we're going to blend the source red and the dest red together, right? And maybe I'll make this 0.8 just to make the math a little easier on us, right? When we blend that dest red in there with the source red, we're going to end up with 0.4, right? We're going to go halfway in between these two because it's a halfway blend according to the source alpha, right? So the resulting color, right, the new destination red in the buffer is going to be 0.4. The alpha channel is going to be something else, right? Whatever we compute, it's going to be something else. Because we were just talking about whatever that, we don't know what it is, we're obviously doing it wrong, maybe. And so it's going to be something else. So there'll be something else in here, right? Now, when we go to do our final thing, because now we've got the screen red, and the screen has no alpha, right? But this is our screen buffer that we're actually going to draw. When we go to composite these two together, right, we wanted it to be the same as if we were compositing these two things, right? This and this. And I guess I shouldn't use screen because we're using source for that. So we'll call this B. For buffer, I don't know, back buffer, let's say. So whatever this happened to be, if this was 0.5, right? What we want to do is this was 0.5 for that gray, and this was originally 0.8. If we were to blend these two together, right, what we would have expected is to get halfway between 0.5 and 0.8, right? If we were doing the blit just directly like we were doing before, right? So what we wanted to get was something like, 0.65 or something like this, right? We want to get halfway. We want to get 0.8 plus 0.5 over 2, right? If that makes sense. So that's a 0.3 difference, a 0.15. So yeah, it's like 0.65. We wanted that. That's what we wanted to see for our red channel. Well, nothing I'm ever going to do is going to produce a 0.65 once this has become 0.4. This is now way too low, right, for that to actually occur. So what can we do, right? There's no, it looks to me like we've backed ourselves into a very problematic situation. And essentially what's going on here, right, is this is kind of like, I mean, I guess I don't know if it's the best motivating case for it, but this gets back to this to do right here, which is someday we need to talk about premultiplied alpha. This is not premultiplied alpha, right? Well, what you can see here is that if we really want to try and tackle this problem, it looks like we need a new way of encoding the color, right? So that when we encode the color, we don't have this problem where we back ourselves into a situation where it doesn't look like we can possibly produce the result that we actually wanted from the inputs to the system, right? And that's where premultiplied alpha comes in. So if you take a look at what's going on in these equations, premultiplied alpha originally came sort of as an optimization. It was an optimization idea. And what it was looking at was the fact that, like, hey, wait a minute. When I do these computations, when I do the blending, you'll notice that I'm always multiplying the colors of the source by their alpha channel, right? We never use SR, SG, or SB. We only use them multiplied by their original values, right? So it's like, okay, why don't I just store the bitmap pre-multiplied so that I don't have to do these anymore, right? Why wouldn't I just do that? And so that I don't have to do those multiplies, right? It's more efficient. And that's where premultiplication really kind of came from initially. But it turns out, if we take a look at that premultiplication, we can actually potentially fix this problem as well. So let's quickly take a look at what would happen if we were to change that encoding, right? So let's say we have the exact same thing again. So we have a source red that was supposed to be 0.8, right? And we have a source alpha that was supposed to be 0.5, right? Like so. And then again, we have that background we're going to do eventually. So we'll do exactly the same setup. So we've got dr and dA here, dr, dA, and we got those as 0 and 0. So let's suppose instead of storing this as 0.8, we store it pre-multiplied, right? So it's already going to be multiplied by its source alpha value, right? So this is already going to be 0.45, right? I'm sorry, 0.4, right? So it's already going to be what it would have been when it's going into this buffer, right? So now, what will happen when we do our alpha blending equation is when I composite, so let's say we were going to do that screen composite. We'll just say, so our final thing, so we're going to skip this step here for a second, and we're going to do the screen composite. So we've got our screen, our buffer that's in there, it's got the 0.5 in it, and we're going to do this composite right now with premultiplied alpha, right? So you already saw me do what that equation was. We're just saying we're getting rid of that multiplication term. So instead of doing the equation down here that we were doing before, where we were saying, okay, so it's going to be 1 minus the source alpha, right, times the buffer plus the source alpha times the source color, right? That's what we were doing before. We're saying this is going to be pre-multiplied, so the actual thing that we're going to compute is 1 minus the source alpha times the buffer plus whatever that pre-multiplied value already was. This is the new equation, right? So we don't multiply by that source alpha. So let's say, right, that we're going to do that. We now get exactly what we had wanted, excuse me, what we had wanted to get before. So, because watch what happens, right? I plug these in, and I get 1 minus SA, which is still 0.5, because 1 minus 0.5 is 0.5, times BR, which is 0.5. So 0.5 times 0.5 is 0.25, right? And then I want to take the source color, which is 0.4, right, and add them together, and I get exactly the value that I wanted, right? It's exactly the right value. 0.65, it's exactly what we said we wanted. Now, how did it do that? It does that because now we're encoding that value that we add directly, so we don't have this problem of having to get a number over 1 to ever produce this actual blend to occur, right? We've pre-encoded that multiplication, and so we can just produce the value directly, right? So that works just fine, just like in the old case, and that would have worked up here, right? And so now, when we do this, when we do an intermediate stage, it will flow through properly. So watch what happens, right? I do the blend here, and I get the exact same equation that we're doing down here, right, is going to happen. So I take the source red of 0.4, I take the destination red of 0, and obviously it doesn't matter what I multiply by 0, so the 1 minus source alpha times 0 is just going to be 0 again. So, and then I add the source red, and so the source red persists as 0.4, right? Just gets put in directly. I don't know what we're calling this. We're calling this dr here. Okay, so dr is 0.4. And then the destination alpha, right? The destination alpha, we know we're in a position to directly see what that should be. The destination alpha, well, I guess maybe not. We'll have to work through another case where this has some destination alpha in it to see exactly what the equation should be for that. So, sorry, I misspoke. So in order for this to still work, obviously the destination alpha, if we wanted this to come out exactly the same, which we do, the destination alpha is going to have to be the same as the source alpha there, right? It's going to have to be 0.5 in order for that to work, right? And then we go ahead and then we go ahead and finish the blend, right? Does that make sense? Because we know that we know that it needs to pass through exactly in this case in order for this to still produce the 0.65 that we wanted. So that we know that in the case where the destination alpha is 0, we want the source alpha to be 0.5. And now we've corrected this problem that we have here. But we still don't know. We need to work through one more case to figure out what we want to have happen if the destination alpha already had something in it, right? So if we go ahead and do one more, so let's say we do the exact same thing again, and we think through what we want that to be. Let's say that we had source R, source alpha, dest R, dest alpha, and let's say that the dest alpha in this particular case was going to be, I don't know, let's say it's 0.5. Let's say the destination alpha is actually 1, maybe. That seems like probably the best thing to try next. I'm going to go with that. I haven't worked out this sort of stuff in a long time, so I'm sorry if I'm not picking the exact right set of cases to kind of show it as easily as possible. That's entirely true. So if we had our destination red of 0 and we had our source red, let's say the source red again is the 0.8, so it's multiplied. It's pre-multiplied, right? So what we would want to have happen here, remember this was originally a source alpha of 0.8 before it got pre-multiplied by its source alpha channel of 0.5, right? So if I had a background that was fully opaque already and there was a 0 in there, right, I would want to produce a result that was a halfway blend between these two color values, right? I would want to say that I want to go 0.5 of the way to 0.8. So I would want to have 0.4 in the resulting destination red, right? 0.4. And certainly I still want to have a destination alpha of 1 as well, right? Because if it was already opaque, it should continue to be opaque at the end, right? So we come through there, and then at the end of that, we would blend against the screen. So the add will still work here no matter what we do. The in source alpha will work exactly correctly, so that blend equation that we were using before works. And the destination alpha, in that case, we would want to pass through exactly because it should produce an opaque blend of 0.4. All right, so now what happens, again, if this was 0.5, let's keep, I don't want to keep having to redraw this tree, right? So you know that we passed through on that case. If we were going to say that it was 0.5, now what should the destination alpha be, right, in the actual result? Because in this case, we're saying, all right, we had something that comes in, it's half, so that we know that the color that we produce should be halfway in between these two colors, right? The original color here we know was also 0 because obviously if the destination alpha was 0.5, it had to be 0.5 times the original color to produce the destination, which would be 0. And similarly here we know it's the 0.8. So we still want to produce 0.4 here. Again, same equation. Nothing particularly confusing going on there. But again, we get into that destination alpha situation. What do we want to produce as the final destination alpha here, right? And so if we had that screen buffer's red, right, and that screen buffer's red was 0.5 as it was before, right, what would happen if we had done 2 subsequent blends on this, right? What we're saying is if we had just done these 2 in series, first this one and then this one, right, what would the resulting color be? And that will tell us what the destination alpha should be to make sure that that gets reproduced, right? And again, that's a little complicated, but thankfully we've got a little more time here, right? We've got about 9 more minutes. Wow, this was almost an entirely Blackboard episode. I picked the exact wrong day for that because the Blackboard thing was, the Blackboard pen is broken. Some days you just don't have any luck, but it's okay. I was sleepy today, so what are you gonna do? All right, so back to where we were at. So if we were to do these 2 things separately, right? Well, we know what we wanted to have happen. So if we were to produce these 2 things separately, when we do the DR-DA blend here against the screen, right? So if we were to do this one against a BR of 0.5, right? Then the color that we would expect to end up with would be 0.25, right? We would expect to get that after drawing this to the screen, because we're doing a halfway blend between 0, the original color 0, and the original color 0.5, right? So we'd expect to get a color of 0.25, and then we would come along and we would blend this guy in there, right? We would say, all right, the SR, the SA, we would expect to blend this in there and say 0.4, 0.5. So now we want a halfway blend again between whatever's in there and 0.8, right? So I'll do the Emacs quick calc there. We basically want halfway blend between 0.25 and 0.8, right? We want to average those 2 guys together. So it's 0.525. So after that next step, we want 0.525. So our goal is, obviously, we can just tell from working it through, we want to produce that as the actual eventual result in this color channel. That is what we need. So given that we know that we're going to come out with a 0.4 here, the question is, what is the alpha value, right? That when we do that equation to BR there, what is the alpha value that would actually produce that, right? Does that make sense? So we need some equation of SA and DA that's going to produce the proper result there. And so to produce the actual color value, again, we're just doing 1 minus the alpha channel times whatever was in the BR plus whatever the incoming color is, right? So when we look at that, we're saying that that result has to be 0.525. We know that the incoming BR there is 0.5, right? We know that the incoming red channel is going to be 0.4. So what we need is something where 1 minus A times 0.5, times 0.5 plus 0.4 is going to equal 0.525, right? And it's pretty easy to see what that would be if we just actually go through this. We end up with 0.5 minus 0.5a, right, distributive, equals 0.125, right? So if I subtract from both sides, I get negative 0.5a equals, well, negative, because it's 0.125 minus 0.5, right? I never am good with math like this, so I always do. So 0.5 minus 0.125, here we go, 0.375, negative 0.375. and divide both sides by the 0.5. So I don't know if you could do last result in quick calc. I bet you can. 0.375 divided by 0.5. There we go. And we get 0.75. Right? So let's just double check that that works properly. So basically, 1 minus 0.25, that would be 1 minus 0.75, that would be 0.25, right? So 0.25 times 0.5 plus 0.4, let's double check. 0.25 times 0.5 plus 0.4 gives us our value, right? So now we got another piece of the puzzle. We know that the alpha value here is going to have to be 0.25, right? So it's starting to look like, okay, well, that's the source alpha times the destination alpha, right? That's just SA times DA. So it kind of looks like SA DA is what goes in here, right? Now we can quick test that, but we haven't really mathematically worked out that's actually true. But we can kind of see where that's starting to go. So if we were to pre-multiply things, that is what would happen. Let's quickly go ahead and change, if we were to do this, right, if we wanted to switch to that pre-multiplied alpha, you can kind of see, where's my loaded bitmap? There it is, debug load bitmap call. So if we wanted to change to pre-multiplied alpha to start to get this working, right, what we would have to do is when we're writing out our destination stuff here, we have to be able to pre-multiply whatever it is that's coming in to put it into this format where instead of storing the colors themselves, we store them pre-multiplied, right? So if I wanted to do that, what I need to do is say, all right, well, the alpha is going to have to be pulled out here, right? First of all, so that we can get it. So we've got to get that alpha value out, like so. So that, like that. We've got to get that alpha value out. And then when we actually do, I guess that's not exactly the way I should do that, because we don't want that rotate alpha shift part. So when we actually get the alpha mask out, this is a little bit weird. So redshift. Okay, so basically this was the place we were kind of getting overzealous with our bit scanning and all that sort of stuff. So this is actually not quite what we want, because what we'd want to do here is actually multiply, is actually get out those channels, do the multiplications, and then put them into position. So really, we don't want what we're doing here, because this puts them directly into position as they get loaded, but we want to actually get them out first, right? So let's go ahead and take that one step at a time. I'm going to go ahead and kill this guy. So if we take a look at what happens now, when we load, that's what we get. Let's go ahead and add that pre-multiplication step here in. Well, let's even just take it one step further, one step slower. Let's actually grab out each individual channel so that we can get what we want out of it. All right. So if I was to do an RGB pull here, right? So I'm going to get the R, G, the B, and the A. What I want to do is I want to shift them down first, which is how we had this code set up originally, but then people were like, you should just shift it directly into place, which is true for what we were doing, but it's not exactly what we wanted. I should have resisted the urge when people said that you should do that. I should have said no. But it was good to show, I guess, how we do it, so that's fine. All right, so we found the least significant bits of these guys, so we know actually what the shifts are for them. We know that you know, in fact, I guess we could say that we've got two shifts here. We've got a red shift up and a red shift down, kind of a thing. So we know that when we shift the red down, it's going to be there, and when we put it back into position, it's going to be there, right? This is green shift up. This is blue shift up. Yeah, and this is alpha shift up. Right? So these scans that we did are what we want to do for shifting down. So really all we need to do is take our mask stuff here and we can just do the shift directly. We don't need that rotate anymore. So when we rotate it down, this is our red shift down, where we're going to grab it out there. We can just go ahead and do that for all the different colors, right? Green mask, blue mask, alpha mask, alpha shift down, blue shift down, green shift down. So we grab those out, and then we just need to put them back, right? So then we just need to say, all right, we've got the R red shift up, like so. The G green shift up. The B blue shift up. And the A alpha shift up, right? Down, down, down. So that, oops, that should produce exactly the same thing that we had before, right? No worries there. Everything's fine. So, you know, we've done the exact same loading we did before. So now all we have to do is do that premultiplication. I don't want to have to talk about exactly how to do a fixed point multiply here. So I'm going to do exactly the same thing that we did in our alpha blender, which is just do the conversion in and out. So I'm just going to say, all right, let's just say that we got these out as reals for now, right? And so I'm going to convert them after we do that into floating point values so we can let the floating point multiplier do it for us, right? So there we go. So we're going to convert those into reals, like so. And then we're going to do that same exact procedure we did before, where we kind of take a normalized version of A, if you will. So we say that we get, we take it and we divide it by 255 so we can produce a number between 0 and 1, right? Now, what we actually want to do is just do that multiplication. So we want R to be equal to R times AN, so that now we're pre-multiplying by that alpha channel, right? And we want to round it after that. So I believe, what were we doing? We already did sort of that in our draw bitmap call. We already sort of were doing that rounding here, and we were just doing it directly this way. So we can continue to do it that way. In fact, we can just copy this exact thing, right? That's exactly what we wanted to do, like so, right? So for our source dest, and then that gets us out of it. The shifts are already baked in there. There we go. So we can get rid of that. We can also get rid of this. Right? So once we actually do this, all we really need to do now is multiply each of these guys by that alpha to get that pre-multiplied thing. Right? And I can leave that out for a second just so we can see if that our function still works when we run it, that we haven't broken anything. And so now if I pre-multiply by that alpha, now I've got pre-multiplied alpha coming in. We haven't changed our blend equation, so things are going to look wrong, as you can see. Everything's got a little bit of a black outline around it, which some people may prefer, but that should be in the source art if we want it, not something that's coming out as the alpha as artifact of the equation. So if we change that pre-multiplied alpha there, now in our draw bitmap call, we can actually say, let's assume that we have that pre-multiplied alpha. So that means we just get rid of these RSA terms, right? Those RSA terms go away. And now we're back to where we started, looking at these guys, right? You can kind of see exactly what's happening there. Everything looks fine, right? And what's interesting too is you'll notice we've already, even though we haven't even looked at what that term should be, we've already gotten rid of that black fringing, right? So pre-multiplied alpha is already working for us, even though we haven't even finished figuring out what exactly we should set the destination alpha to. We're already just accidentally, because pre-multiplied alpha is just easier to work with in that way, we've already actually gotten better than what we kind of had before, right? All right. So what we were saying, what we were saying back here is that, well, okay, we know that this is SA times DA, that's what that is, but of course it was 0.5 and 0.5, so at some level, you know, it's a little bit odd to do the calculation here, because we don't know. This could have been 1 minus. It could have been, the equation that we wrote here accidentally, just from before, could actually be right, because in RSA, 1 minus 0.5 would also be 0.5. So this would end up being essentially SA times VA plus SA or whatever. So this may actually be the right equation that we had ended up with here. We need some way of actually figuring out what that should be. And so what I'd like to do is just do exactly what we did with the examples here, but do it with algebra, so that we kind of can see what we actually want the result to be. Now, this is going to get really messy, and this is why I said I picked exactly the wrong day to do this, because the Blackboard pen is not working properly, and what can you do? But, I mean, you got to do what you got to do. We want to finish what we started. So you saw me work through these examples to kind of show you how things are going to work. All we really need to do, if we want to figure out what these things should be, is just not use numeric values, like pass through the actual terms, and then we should be able to solve for what that composited version is. We should be able to see what the math works out to be, right? That's what I'd like to do here, and it's going to be ugly, but what are you going to do? Nothing, I guess. So let's set up the motivating situation. I'm not going to use color and alpha and that sort of things. I'm just going to maybe use, well, you know what? I'll use C for color, and I'll use A for alpha, right? And so we have several of these things coming in. So we've got two of them. Let's say we've got C0, A0, right? And then I've got that's going to be like bitmap 1, right? Then I've got C0, C1, A1, and that's going to be bitmap 2, right? I guess I should say bitmap 0 and bitmap 1, right? And then I've got sort of the screen, what was on the screen. I've got C screen, A. Well, we don't have an A screen, so that's just what's on the screen buffer. And then I've got the intermediate buffer, right? So I've got C, whatever that intermediate, we'll just call that B for now, right? Alpha buffer. And this is that buffer intermediate. So if we look at what happens for the screen blend, right? That we know exactly what that value should be, and that's the motivation we're going to use. So if I was to draw bitmap 0 on top of bitmap, bitmap 1 on top of bitmap 0, right? Then I know what we want to have on the screen. So the first step of that, right? The C screen, the first step of that, I'll call that maybe C screen prime for now, because we're going to do 2 steps compute it. The first thing for C screen, the screen won't have anything in it. So it's just going to be that blending. Remember, the blending equation is 1 minus alpha times dest plus source, right? That's the premultiplied equation that we worked out before. So that's what we're doing in here, right? So the color, we know, is going to be 1 minus alpha times dest, but there's nothing in the destination yet. It's empty, right? So 1 minus alpha times dest plus whatever the source color actually is, right? Whatever that source color actually is, okay? And so that's going to just be color 0. That's going to go straight in there, because remember, these are pre-multiplied. So these guys are already pre-multiplied, right? As is this guy, right? So that's what's supposed to happen there. The next step to get CS, right, is this is what's in the destination. That's this, right? So we're going to have 1 minus whatever bitmap A's alpha is. We're going to have 1 minus alpha 1. Gosh darn it. Man, the pen is killing me today. We're going to have 1 minus whatever that alpha is times what was in the destination, right, which is C0. And then we want to add to it whatever our source was. Stream has ended. No, it hasn't. I beg to differ. We're going to add to it whatever our source was, and that source is C1, right? Like so. So that's what's in the screen at the end of this process. When we look at what that is, we can actually kind of see this is what we wanted that alpha to be, right? I believe. Yeah, it's 1 minus alpha 1 is what we would expect to see. Did I do everything right here? CS C0. Yeah, looks to me like, yeah, because alpha 0 is not involved because what was in the screen is not. I wonder if we have to do one more stage of this to get it. That's unfortunate because now that I think, yeah, well, okay, we'll see. So we want that to equal this, right? This is the end goal, right? If I haven't made a mistake there. So if that's the end goal, now what happens when we build that pre-buffer? So we go through and we do this in 2 stages. This would actually be the color that's in the buffer at the end of things, right? If that makes sense. So this is CB as well, right? CB, if we did 2 steps of alpha blending, would also be this. So when we then go to draw to the screen, right, we're going to go through another pass. So our C screen when we're using the buffer, right, our C screen if we're using the buffer, in fact I could basically do that. This is what's going to be in there. So our C screen we want to be equal to this, right? This is the target that we want it to be equal to at the end. But what it's going to actually, it's going to go through the equation 1 minus the buffer's alpha, whatever's in that, oops, sorry. 1 minus the buffer's alpha, right? Times whatever was in the screen to begin with, right? Which we know in this case, all right. Man, I'm too sleepy today. So in order to actually do this correctly, right, I've got to actually have something in that screen to begin with, is the problem. Because as I got down there, I'm like, okay, that term goes out to 0, and then I can't show anything. So, all right, let's try that one more time. Right, these are pre-multiplied. Okay, and this has got to be pre-multiplied as well. One more time. So we have to assume that there's something in the screen to begin with. And so, yeah, like we're going to have to change the nomenclature. So we want a result screen, right? This is the result, let's say. Or I should say color result. That's how we're doing that. So this is the result we actually want. Okay. All right, one more time. So the result we want is going to be the process of doing those blends, right? So it's going to basically be if we imagined our lerp here, right, our blend equation or whatever, it's going to be a blend of whatever the thing that's in the screen right now, right? We'll do well, let's do source dest. So it's going to be a blend of C0 or C1 on top of a blend of C0 on the screen, right? So whatever's on the screen at the moment, right? So expanding that out, and again, our blend, right? Our blend for source and dest equals that 1 minus the source, the alpha for the source, times the destination color, because we're doing color destination, and that is plus whatever the color of the source is, right? So that's that blend equation that we're using. So if we expand that out, we get CR equals the blend equation for color 1, and man, it's hard to draw with this pen. And then we're going to do this equation for that back part. So we get 1 minus the alpha of the source, and again, this is source dest, so that's going to be alpha 0, and that's going to then be times the color of the screen, the color of the destination, plus that source color, so C0, right? So that's the blend. So the result we want, out one more step, we've got the blend now. So out one more step, the blend is going to be, again, same equation. It's going to be 1 minus the source alpha, and again, this is the source, right? So alpha 1 times that destination color, and that's the destination color there, right? So we've got 1 minus A0 CS plus C0, right? And then that's going to be plus whatever that source color was, right? So that's going to be plus that that color 1, right? Did I do that right? Let's see. Am I saying? I think that's right. Yeah? Fifth of the link, okay? So that's what we're looking at, right? And you can see that the result here, right? If we were to multiply this out a little bit more, let's just group the terms, right? So 1 minus A1, if we do the distribution inside here, we would get CS minus A0 CS plus C0, right? Plus C1, like so. And so if we were again to multiply out again, it's going to get super ugly. I might even check the stream for catching my math errors, because I'm very bad at multiplying out things like this. I think I've said that many times on the stream. It's true. CS minus A0 CS plus C0, right? And then we've got the minus A1 version of that, right? So we've got minus A1 CS plus A0 A1 CS plus, oops, sorry, minus A1 C0, all multiplied out, plus C1, right? So now if we group the terms, if we group the terms together, we can kind of see, I guess, what, we can see this a little more clearly. If we group the terms by their alphas, which is what I was kind of hoping to do, you can see there's three bear colors here, right? So all of the colors themselves get added in eventually, right? You've got a CS. Well, you know what? Maybe we should group them by. Maybe I should just group them by color. Now that I think about it, that seems like a smarter way to analyze this, right? So if I group them by CS, right? My CS term would be 1 minus alpha 0, right? So that's the CS term here. CS term here. Minus A1, minus alpha 1, plus A0, A1, right? Those are the terms that are on there. 1 minus A0, 1 minus A0, minus A1, plus that, right? Then if I group for my C0 term, my C0 term is just 1 minus A1, right? And then my C1 term is just C1. There's nothing happened to it because it was the last guy on top, right? And so I can pull that out a little bit further as well. I can say CS. If I look at this thing here, you've got the sort of well, I guess I don't know if there's any real reason to pull that out, but you can kind of see if I was to pull out I could do sort of an A01 pull out or a thing here. I don't know. It doesn't look like there's anything actually all that useful to pull out here. But this is what the result should be, right? This is what the result I actually want to get, right? So let's take a look at what happens when I actually am going to produce this buffer. So I want to get this out, this kind of super gnarly ridiculousness that I've got here, right? I want to get this out, and I have this equation to work with, right? So what we're going to do at some point at the end of the pipeline is we're going to apply this equation, right? Blend source dest. And the source and dest is going to be my precomposite buffer, right? So this is going to be the source. I want to blend that source color, that buffer color, with the screen, right? With CS. And somehow, using that, right, which is going to be equal to that blend equation, which is 1 minus whatever that alpha is for the buffer. This is the thing that we don't know, right? 1 minus AB times the color that's on the screen. I want to have that plus that input color from the buffer. I want to have this magically equal this, right? Somehow. Now we know that the color from the buffer basically has to encapsulate these terms, right? Because the color, the color from the first bitmap and from the 0th bitmap and the first bitmap, that's not represented anywhere in the screens thing. So that has to come through entirely here. Now, that's the trivial part because we already knew that that's what the buffer's color was going to be, right? That's just the blend, all that is the blend equation for C1 plus, for C1 over C0. So we already had that, right? That's this right here. We already knew that that was what that was. We didn't really have to do anything there. We already knew that's what that was, right? So our CB term is exactly what we thought it was. It's just 1 minus whatever the incoming source alpha is, right? So the source alpha times the depth color plus the source color, right? That's exactly what that is. There's the source color, there's the source alpha, there's the depth color, right? So it's exactly right. So we know CB, we did it correctly, it's exactly what we want. The question is, what do we do with this nonsense up here, right? For our source, this is what that says. So this suggests that the equation for producing our AB, right, is we're saying this term, CS, we need this to reproduce that. We need 1 minus AB to somehow reproduce this ridiculousness right here. We need that to produce 1 minus A0 minus A1 plus A0, A1, right? Solving for that, what we would get is 1 minus AB equals 1 minus A0 minus A1 plus A0, A1, right? We want to solve for AB, so we got negative AB equals, of course, the 1 is subtracted now, so that removes that 1, right? So we just end up, we get rid of those two, and we get A0 minus A1, sorry, minus A0 minus A1 plus A0, A1. And we want to negate both sides, so we get AB, right, equals A0 plus A1 minus A0, A1. And yes, after an hour of math, ladies and gentlemen, we come to the equation for the premultiplied alpha that will give us the result that we want, which is A0 plus A1 minus A0, A1 star if Casey didn't make a typo, didn't make a, I don't know what you call that, a math O, which I almost always do. But that would be assuming that we worked out the math properly. That's what that was. And you saw I did that there, right? It was a ton of writing, but there was nothing complicated. All I did was just say, if we were to do this procedure that we'd worked out by hand a couple times, and we just let the math flow through it, what comes out the other end, right? And the answer is that. And if we were to type that in, right, all that's saying is, all right, the result for the alpha, and we have that sort of space issue here where we're going to multiply these two things together, so we actually need to be able to do some slightly more complicated stuff here. So, excuse me, this C alpha complicates our life a little bit, if you know what I mean, because we haven't thought about what happens if we need to sort of introduce this additional blend in there. Because what we really would need to do is, since this is pre-multiplied alpha now, that C alpha is going to have to be accounted for. But let's ignore that for 1 second. So let's do to do KC, put C alpha back in, right? Okay. So, because we were only using that to modulate our shadows. But anyway, so let's say we're going to actually try to implement this now. So now if we imagine ourselves having both of the alphas in the 1 to 0 space, so we can actually work with them as simple floating point values, right? Then we have this equation. It's A0, so that's SA, right, plus DA, I did this wrong. That's that, right? RDA. There we go. So it's RSA plus RDA plus the two of them times each other, or sorry, minus the two of them times each other. That's the actual alpha in 0 to 1 space. And then so if we need that to go back up into 255 space, it would look like that, right? So again, the source, the dest, and then subtract the two of them multiplied together, right? I don't know if that makes some sense. And so that is the actual equation that we would want for our destination alpha. And as you can see, also, it produces those nice non-darkened edges now, and everything works correctly everywhere it would appear, right? Although we do have now the issue of C alpha, which we need to fix. All right, so let's go ahead and re-enable our draw test ground stuff, just so we can see what's going on there. So let's go ahead and turn that back on, like so. And I guess our grass tufts were still always in there. So now we're compositing with premultiplied alpha properly, which means our edges are all handled correctly. And you can kind of see that, looking nice in there. Of course, we do still have hard edges here, but that's to be expected. That's just clipping, right? Our bitmap, this is the whole size of our bitmap. So there's nothing we can really do about that. When we're actually producing them, we're going to let them keep going, obviously, right? So that's proper. And we can also go back to doing our draw test ground only that one time, right? So now we're back to full speed as well, and everything's good. So that was an extremely long meander, but we needed to talk about premultiplied alpha at some point, and now we have. And the premultiplied alpha is now working properly for us, and we don't have those dark fringes on our bitmaps, which is what we want. Too bad the pen didn't work the whole time, but what are you going to do? Sometimes the worst things happen at the worst times, and that is, I guess, the motto of Microsoft Windows, one might say. Okay, so that means we can go ahead and get rid of our someday talk about premultiplied alpha, because we just did. And now we are also, at least as far as we know, if I didn't make a math error, doing the alpha correctly there. But we want to put in this C alpha. Now, to put in that C alpha, remember, all of our alpha now has to be pre-multiplied, right? And what that means is that this C alpha is a new pre-multiplication term we have to put in there, right? And so when we compute the alpha here, and if we multiply that C alpha in like we were doing, to sort of add an additional modulation so that we can make things be more transparent than they would ordinarily be, what we have to do is we have to take these colors and also multiply them, right? C alpha has to multiply everything because everything needs to be pre-multiplied. So that is, necessary if we want our pre-multiplication to work. And you can kind of see now our shadows are back to sort of modulating based on height like they were doing before, right? All right, so that was not the way I would have liked to have done that. I would have liked to have had a working pen that whole time. But there you go. And that is literally, like, I didn't know that equation ahead of time. I mean, I think I probably knew it I probably have used it once or twice when I've been writing some bitmap code, right? But I literally figured that out on the stream, totally honest. I did not look it up beforehand. So that is what it looks like, literally, when I need to figure out an equation, right? And so if you go back and think about the steps that I went through, it's kind of good to internalize them. Work through some examples first. Like, see what the process is and make kind of a little tableau, if you will, of here's the process that we go through, right? Then go, okay, I see what's happening in the process. And again, I shouldn't say, it's not like figuring out that pre-multiplied alpha is a thing. I knew that was a thing, right? And figuring out pre-multiplied alpha is like
hey, you're a rocket scientist or something, right? The people who figured out premultiplied alpha and that it was important, that took a lot of people a lot of time and looking at things to do, right? So not that part. I'm just talking about, you know, there's a thing that you want. How do you get the math out for it, right? And so working through the examples, that's the first thing. Seeing how they should go. It gets you warmed up and it kind of gives you something you know that you have to match. And then just seeing, can you write the equations so that things just flow through the equations so you can just solve for the value that you want. And then, you know, that is obviously the most straightforward path and the easiest one to do. Sometimes you can't do that and then things get more complicated, but assuming you can, that's what you go. And then you end up with hopefully the right answer. What we really probably should do here is actually check the math, right? Go back and plug some things in and make sure that it works out the way that we wanted. If we didn't have any way of checking it, otherwise that's what we should do. What we could do is like destination alpha equation for premultiplied alpha and just check ours versus someone else's. But I don't know if there's really any way to find that out. If that makes sense. What we really want is like Sean Barrett's article on premultiplied alpha. So yeah, maybe I won't do that now because we've already been quite long. So yeah, so what we need to do, like the last step is we need to go like check this for math errors, because like I said, oftentimes when I work through math like that, I can't just assume the result that I got was correct, because oftentimes I will make a mistake. And so what you want to do is you want to go through and like retest the equation using the examples that you worked through before. Make sure they get the right answers that you think you should have gotten. And also, obviously, if other people have worked it out beforehand, go check against theirs, et cetera, et cetera. And you might ask the question, well, why would you rework out an equation that someone else already worked out? And the answer is because if you don't practice working out equations that other people have already worked out, you're never going to be able to work out equations that other people haven't worked out. And so especially on simple cases like that, where it's not particularly hard to work them through, you should work them through until you start getting to the point where you can do them reasonably well, right? And if you're lucky, you're better with math than I am, and you don't make as many careless errors when you're working through the equations, right? Because some people are much better at math than I am, and that's a big help too. You can also use a computer algebra system to do it. Like you could plug it into Wolfram Alpha or Mathematica if you have that, or MATLAB. Sometimes those have symbolic solvers in them, and that can help you check or actually just do the math follow through. So once you've set up the problem properly, you can have it chug through it for you and produce the result. So that's pretty good. All right, let's go ahead and do the Q&A. So if anyone has any questions quickly, we've got about we can do some quick questions before ending the stream. And let's see if there's any questions out there. It's too bad pseudonym 73 isn't here today, because I think he's the resident math expert, and so he could tell me if he would have caught any errors. According to a link they posted, to fix the Wacom driver without restarting, stop and start Wacom Professional Tablet Service. Okay. Wacom Professional Tablet Service. Stop the service. Start the service. Okay, I have done so. And maybe I will plug in the tablet again, just to give it a fair shot there. And let's see. That did absolutely nothing. We can try reloading Mischief. No, that did not help, unfortunately. I'm assuming that if I reboot the machine, it'll help. Of course, that'll kill the stream. Oh, no, there we go. So it did help. It just, Mischief had to be rebooted because maybe Mischief didn't think. Oh, no. It worked for a second there, and then it seems like Windows like overrode it. Oh no, now it's working? I don't know. Okay, yeah, okay, it is definitely working. Cool. Thank you very much for that. That was very helpful. Being happy, sleepy, and sneezy, do you realize you're just 4 dwarfs short of a whole crew? Well, actually, I would say I'm grumpy, sleepy, and sneezy. Because honestly, that tablet thing, like I had to do all this math with a non-working tablet, was pretty annoying. I mean, that's a lot of drawing. It was a Blackboard episode today. So like, on days when we do a Blackboard episode, I kind of wanted to have the Blackboard working. That seems like a pretty reasonable thing to ask for. But you know, nowadays, nothing works reliably anymore. Mr. Fourth Dimension. So if I understand correctly, sorry if my interpretation just confuses anyone, but the reason off-screen rendering was incorrect before premultiplied alpha was that after blending things in the texture, the colors there were pre-multiplied because they were multiplied when they were put in the texture. If for some reason you didn't want to optimize your code, you could also divide the color channel by the alpha to get it back to unpremultiplied. Is this a reasonable understanding of the issue? So it's more that you can't really make the math work out properly without the multiplication being pre-multiplied, right? The problem is actually a little bit deeper. It's that, I'm trying to think of what the right way to say it would be. It's the way that Sean Barrett typically says it, and really, like, if you want the full technical explanation, he's the guy. The way he usually says it is something like, you know, non-premultiplied alpha. Wish we had a better term for it. Premultiplied alpha does not distribute over linear interpolation. I think that's the way he normally says it. And basically what he's talking about is that if you want to stack linear interpolations on top of each other, right? So I'm going to do, you know, that blend equation, right? So I'm going to do a blend of a blend, right? Or blends of blends and so on, you know, right? I guess I probably shouldn't use those. Okay, X, Y, Z, W. There we go. So if I'm going to do blends of blends, right? You can't actually make the math work out properly because if you don't pre-multiply the alpha, then the blend doesn't distribute, right? Meaning you can't actually compose blends in arbitrary ways like this unless the alpha is pre-multiplied. So I believe that's how he usually phrases it. I've never really worked out. In fact, that's the first time, this right here is the first time I ever even solved this equation, right? The first time I've ever done it. So I've never really thought about it too much beyond just knowing that it was the right technique, but I don't do that much work with it. In fact, recently was the first time I think I ever even really actually used this knowledge in an actual blending thing. Now, maybe I've done it once before, but usually preserving destination alpha, I don't do. So this is the first time I'd ever really done that, preserving destination alpha. I think I've done it maybe one time before, but I never actually worked it out all the way through like that. And so there you go. So I haven't really thought too deeply about the meaning of that. But that is what he was sort of talking about, and he's been advocating premultiplied alpha for decades now. And he's the reason I originally even knew about premultiplied alpha, because actually for a long time, game industry people didn't know about premultiplied alpha, and you'd get those black fringes on everything. There are old games where you actually get black fringes on the sprites because they didn't do premultiplied alpha. And once MIP mapping, like MIP mapping on graphics cards, MIP mapping is a blend. MIP mapping, well, it's not a blend, but I shouldn't say that. Bilinear filtering. You don't even need MIP mapping, right? Bilinear filtering of textures, like when you have textures and you're sampling like there so that you get a blend of the 4 colors, of the 4 texels, that's 2 of these, right? It's a blend between these 2 colors, and then you blend the 2 results together, conceptually speaking. So it's a bunch of blends, and then that gets blended to the frame buffer, right? So you have this series of blends that goes on with texture filtering, and you would get these black fringes on your sprites. And the reason is because you need, in order to have this work out properly, if you're doing that lerp, if you're just using that linear interpolation over and over again, you need it to distribute properly, right? Now, like you kind of hinted at with your question, you could always probably make the math work out by like you said, like redividing every time. So you try to reconstruct what the color was. It seems like that should work out. And probably the reason that you never actually do it that way in practice is because like you're working with hardware that does this sort of stuff, and you don't have the opportunity to go in there and tell the hardware you want to do this redivide. Not only that, but like you said, the efficiency would be a problem. So I suspect that yes, what you were saying is correct. You could just work out the math the other way and constantly be doing more work to your colors to put them back into a space where they could blend properly. So like you said, do a divide out, do the thing, put it back in. But that runs into problems because eventually you're going to have to be working with hardware that has some fixed notion of what those blend equations are. So even if you didn't care about performance, you're probably in trouble because you wouldn't be able to do it. Now, maybe you could just turn off, if you really didn't care about performance, maybe you could still do it that way and just turn off the texture filtering hardware entirely. And you just take samples yourself and do the divide out and whatever. So it'd be entirely, you just program it all, do it all in shaders, right? Maybe that would work. But typically you want to take advantage of that fast stuff as much as possible. So I don't know. Let's see, any other on-topic questions? Let's see. Can you give a small example of what the decompression step between sim entity and stored entity will look like? Probably not, because I don't know what it will look like yet. We're gonna have to actually get there first, and then see what we want it to look like based on the situation. Drive 137, maybe we should set a way for you to see things like that kind of help if someone finds a good possible solution. No, I don't know how. Sorry, Drive 137, I'm not sure what that was in reference to. So it looks like we don't have any other questions here. Math dense streams tend to not have very many questions. I feel like that means probably people don't pay very much attention to when I do the math workouts. Maybe, I don't know, or maybe everyone's much better at math than I am, so they're just like, yeah, I totally get it. It's totally fine. We're done. So yeah, that's fine. But yeah, a lot of equationing today. Look at all that. Man, I wish this had been with a good pen. Now I know, though. Thank you for pointing out to me how to fix it. So that's good. So you know, at least now I know to start and stop and restart the service, and then that fixes it. All right, so let's go ahead and wrap up the stream for today. We've got our premultiplied alpha in there. We want to check this math for errors at some point to make sure that we've got it properly. But now we are doing pretty much everything that we needed to do. So we pretty much got our precompositing working. Now, again, we don't really have much of a use for that precompositing at the moment because this was kind of just an aside that we decided to go down because someone got ran over by a train. If you want to be completely honest, that's basically the history of it. Someone got ran over by a train, and so we decided to go ahead and take a little diversion into some background compositing. And I think I'm pretty happy with how it came out. We learned about premultiplied alpha, and we fixed our pipeline to use it, so that's a good step. We definitely needed to do that. There's still a little bit more left in there that we gotta talk about, like gamma and stuff, but we'll deal with that when we get to the renderer. But yeah, so our compositing works, and honestly, it looks pretty good already, even though there's no logic in here, so it's kind of random. It actually, you know, like I've seen game ground textures that look worse than that, to be completely honest with you. So I think that's pretty good. That validates my assumption that basically when we start to do logic for how we want the ground to be laid out, I think it's going to work just fine and composite properly. So that's pretty good. So hey, that was a good unknown that we got cleared up. I'm pretty happy about that. So starting next week, we should go finish cleaning up our collision detector. I suppose I maybe prematurely closed this. I should probably grab up our to-do list here. So next week, I think, will be the week that we finish out Z. So what I'd like to do next week is kind of get our Z worked out again, where we kind of have grounds and stuff properly done, and just kind of have a relatively stable idea of what's going on there so that we don't have any more confusion about that. So next week, I think let's go ahead and finish up the Z. And then the week after that, I think we should go ahead and tackle the collision detector. So I think we probably want to do this exactly as we kind of were doing it before. And then multiple sim regions per frame. Yeah, I mean, I would basically say that this is the hard stuff right here. So I'd say we want to probably go ahead and try to just bear down for a couple more weeks and finish up all that. And then I think we're in pretty good shape to just go ahead and cruise through all of these things here, which are much more straightforward. These are pretty rote. They don't involve a lot of experimentation. They're pretty straightforward. There's really not a lot to them. This is mainly just a lot of code typing in, right? Because they're very, very straightforward things. So I think we'll kind of sail through those pretty cleanly. Yeah, and that should be about that. Now, looking at how we do this, I'm just kind of seeing how we probably want to go through things. Animation, AI, this is definitely, so I would say we probably have, we probably have something, yeah, I mean, looking at it this way, this probably looks roughly like how we'll tackle them in order to. I don't know. I mean, like I said, I don't really make schedules too much, so we'll tackle them in whatever order they come up, but just looking at the things that we want to do, it looks like this probably isn't really too far off. I think this looks basically what we'll go ahead and what we'll be doing to get to production. Yeah, it looks pretty reasonable. And so we'll go ahead and we'll push through some of this hard stuff. We'll get our debug code working so that everything from then on will kind of have a nice set to it. This probably needs, we haven't talked about fonts here, so we're going to need fonts, because otherwise we're not going to be able to do any debug code. So I think this looks relatively, I think this looks relatively good. I'm pretty happy with it. So next week, we'll probably go and try the new time slot like I was talking about. I'd like to maybe try doing some 5 p.m. Eastern Daylight Time streams. So I think we'll do 5 p.m. slot next week and see how that goes. See how much of a problem it creates for people who are on the West Coast. I think everyone else is probably pretty okay with it, but West Coast it's a little more problematic because it's close to work time. But we're gonna go ahead and see how that goes as a little bit of a test, I think. and we'll make a call from it after that. Anyway, as always, if you would like to pre-order the game and follow along with the source code at home, because it comes with all the source code, you can do that at handmadehero.org and use the pre-order button to do that. It, again, comes with a link you can use to every day download the source code that I've been working on so you can play around with it yourself at home, and that's a good way to learn from it. Obviously, we have a Patreon page if you want to support the video series. We have a news and forum site that you can go to for asking questions or getting ports to other platforms, things like that. There's an episode guide on there. There's also the tweet bot, which sends out the schedule, which is handy if you want to know what the schedule is going to be. Check that tweet bot out. And we should be back here at 5 p.m. Pacific Daylight Time on Monday. So I hope to see you all there to try out the new time slot. We'll see how it goes. Or if it's a giant panic, we will see. So I hope to see you there. Have a great weekend and enjoy the pre-multiplication of it all. Enjoy your pre-multiplied weekend, brought to you courtesy of Handmade Hero. Thanks, everyone.